Good evening, Barry. This is the end of everything, and it sounds like we have a new arrival. So this evening we're going to eternity and beyond, to paraphrase our old friend Buzz. We'll be, after a little prologue, looking at the future of the Earth, the Sun and the solar system, and the far future of the fate of stars and galaxies, and the far, far, far future looking at the ultimate fate of the universe. And in order not to leave you too depressed at the end of all of that, I will summarise with a little epilogue right at the end. So I'm not going to talk about how everything began, because this is the end of everything, not the beginning of everything. But just to give a little bit of context, we think the universe began some 13.8 billion years ago. Everything that we currently see in the observable universe, some 90 or so billion light years in diameter, because the universe is expanding, we believe everything used to be an awful lot closer together. And you can imagine a time when everything that's currently inside the observable universe used to be only centimetres apart, what you might think of as a cosmic golf ball. That produced an awful lot of matter. All of the hydrogen in the universe was made in the first 3 minutes or so, and the universe from that point onwards expanded and cooled. But that's history. We're talking about what's happening from this point onwards. And in order to try and keep some sort of track as to where we are in time, I'm going to use this timeline along the top of the slide here, where each box represents 10 times further into the future. So we can think about 100 or 1,000 years into the future, and we can keep going all the way to 10 to the power 12 or a trillion years into the future. So I'll be using this 10 to the power notation, otherwise we just get too many zeros. So think of this, if you like, as 10 to the power of the number of zeros in the number we're talking about for years into the future. And I'm indebted to the work of Adams and Laughlin, who published a paper, some quarter of a century ago now, on the timescales on which various astrophysical phenomena are likely to occur. And I've used that paper to try and get my slides in the right order. I'm not necessarily talking about the Earth and then about the Sun and then about the galaxy. I'm looking at things that are happening on particular time frames, and I'm trying to put them in the right time order. So let's jump ahead a few years. I'm not going to worry about the next 100 or the next 1,000 years. Let's assume that we don't destroy ourselves with nuclear war. Let's assume that man-made climate change is under control. Now, we know stars are going to change on timescales of 10 to the 4 years, but we can't tell really which stars are going to end their lives in supernova. But on this same timescale, we can tell that changes are going to happen to the Earth. For instance, we know the Earth's axis points to a particular point in space, and it traces out a very large circle, so-called precession, on a timescale of 26,000 years for this cycle. That means the pole star continuously changes. At the moment it's Polaris, but in the past it might have been Tuban back in the Egyptian days. And in another 10,000 years or 12,000 years or so, the North Star is going to be Vega. The North Pole is going to be very close to the bright star Vega. So that's going to make it much easier for Boy Scouts to point out which way is north, because the North Star will be the brightest star in the sky, or at least one of the brightest. Some people seem to think Polaris is, but no, Vega is going to make a very nice pointer to north. But there are going to be consequences for that. If we think of the situation at present with the Earth's axis pointing at Polaris, we are nearer the Sun during northern winter. We are nearest the Sun, perihelion, in the month of January, which for the north is winter. But if the Earth's axis points in the other direction towards Vega, then we're going to be nearer to the Sun during northern summer. And so the tilt of the Earth and the distance to the Sun are going to produce slightly more exaggerated seasons. Variations in the Earth's climate due to changes in the Earth's spin or changes in the Earth's orbit around the Sun are collectively called Milankovitch cycles, and we'll think about that again in a little while. On a timescale of 10 to the 5 years into the future, the Voyager spacecrafts are going to pass close to other star systems or pass through other solar systems. If you remember, Voyagers 1 and 2 were launched back in the late 1970s, and they are now heading out of the solar system. If we think of the directions they're heading, at the top there, Voyager 1 is heading off in the direction of the star system Gliese 445. And on this timescale, it will be passing through that solar system. Voyager 2 at the bottom of this image is heading off in the direction of Ross 248. And on timescales of order 30 to 40,000 years, it'll be passing through that system, and assuming nobody picks it up at the time, it'll pass through the solar system and head on to the next solar system. Also on this diagram are Pioneers 10 and 11. They were launched a little bit earlier, back in the early 70s, but they were travelling more slowly, so they will take a little longer to reach their destinations. Pioneer 10 on the right-hand side of the image is heading off in the direction of Aldebaran. Pioneer 11 on the left side of the image is heading off towards the centre of the galaxy. Still on a timescale of 10 to the 5 years into the future, we know from historical records that the Earth has been through ice ages, repeating cycles of glaciation and so-called interglacial periods where there's a little bit more warmth around the Earth. These tend to occur on timescales of order 100,000 years or so. Earth entered an interglacial warm period relatively recently, and so the next ice age, you could say, is due on a timescale of order 100,000 years. And this is another manifestation of Milankovitch cycles, changes to the Earth's orbit. Still on a timescale of 10 to the 5 years into the future, we know the Earth's rotation is slowing down. In a separate talk I give about why we need leap seconds, I describe how the Earth is slowing down its rotation and the days are getting slowly longer, which means to keep our clocks synchronized with the Earth, we've had to introduce leap seconds quite a few times over the last few decades. Adding a leap second keeps the clocks synchronized with the slowing Earth rotation. But in 100,000 years into the future, it's been predicted that the Earth will have slowed down sufficiently that rather than adding a leap second every few years, we would have to add a leap second every day. In other words, the length of the day would no longer be 24 hours, it would be 24 hours and 1 second. That slowdown of the Earth, because of the pull of the Moon, will continue, and we'll come back to this a little bit later. Still about 10 to the 5 years into the future, we can't predict when supernovae are going to happen, but this particular star, Eta Carinae, visible in the southern hemisphere, is very massive and appears to be very unstable. It has a nebula around it, which is basically the outer atmosphere of the star that's been shrugged off for the last few thousand years, possibly even longer. So we know that the star is having difficulty hanging on to the outer part of its atmosphere, and it's producing this nebulosity in its immediate vicinity. Perhaps this is a sign of it getting very close to the end of its life and possibly going supernova on these sorts of timescales. We can't predict when, but it's been predicted that it will go sometime in the next 10 to the 5 years. It might be beaten to the punch by Betelgeuse. Betelgeuse visible, of course, in the northern hemisphere. Here's an image of a night sky in which the photographer has artificially brightened Betelgeuse there in the top left-hand corner of the Orion constellation, and this might be what it looks like when it decides to go supernova. Betelgeuse at a distance of 600 light years, it will be spectacular, but not necessarily dangerous for us at that distance. But there are other possibilities that could be a danger to Earth. For instance, there are Wolf-Rayet stars. These are very unstable stars. They are rapidly rotating systems that produce jet systems. This particular one, Wolf-Rayet 104, is 7,000 light years away, some 10 times further than Betelgeuse. But it's thought that when this one decides to die, its death may result in a radiation burst even more powerful than a supernova. Because of this rapid rotation, these systems form jets, and if we're unlucky enough to be pointed to by one of those jets. The jets are only a few degrees across, and we'd have to be rather unlucky for one of those jets to be pointing in our direction. But if it happened to be so, then it could be serious for life on Earth, the sheer amount of gamma ray radiation that we might receive. Moving forward 1 million years into the future, we've got a pretty good idea how stars around us are moving, because the Gaia spacecraft for the last decade or so has been measuring the positions and the motions of stars as they move around the galaxy. We spend something like 200 million years to go one circulation, one rotation around the galaxy, and all the stars around us are doing pretty much the same thing. But because we're all in independent orbits, every once in a while we might come close to one of our neighbours. And by looking at relative motions of stars, it's been predicted that one particular star, Gliese 710, might end up getting rather close to us. So our sun on the left-hand side there is surrounded by an Oort cloud, a cloud of trillions of small icy particles. I say small, but they are large enough that if disturbed by this star getting close to us, as indicated by this graphic, it could disturb the Oort cloud and send huge numbers of these icy bodies raining down into the inner solar system. It's been calculated that perhaps when Gliese 710 comes our way, it could result in naked eye comets, perhaps one every month for millions of years. This could be a problem for us in the future. But it's interesting to note that for a little while, our solar system will have 2 suns, just like other systems that we are aware of, like, for instance, Tatooine. Still on a timescale of 10 to the 6 years into the future, here's a picture of Meteor Crater, Arizona. You might think that this picture is here because we might expect an impact like this every 1 million years. Well, that's not why the picture is there. One, it's to remind us how lucky we were that this impact just missed the visitors centre. That was one stroke of luck. But the other point is that on a timescale of 1 million years, we would expect any impact similar to this to be effectively removed from the record of seeing them in the face of the Earth, seeing them in the Earth's crust, because of weathering. Wind and rain will weather down structures like this, and any crater similar to this that was made more than 1 million years ago, it would be unlikely that we can still see evidence of it. You might say, well, yes, of course, that will happen on the Earth because we have weathering systems, but it won't happen, for instance, for craters on the Moon. Well, yes and no, because the Moon is not as eternal as you might think. For instance, footprints on the Moon left by the Apollo astronauts will eventually disappear. Not through weathering in the same sense as on Earth, but the Moon is being constantly pulverized by micrometeorites, which are effectively stirring up the regolith, the soil, if you like, on the surface of the Moon. And that means all evidence of the fact that man has visited the Moon will eventually disappear through this micrometeorite effect. Weathering, if you like, but through micrometeorites rather than wind and rain. Moving 10 to the 7, 10 million years into the future, we can think about what's happening to Pioneer 10. We know it will pass through star systems on timescales of order 30 to 40-ish thousand years. So on a timescale of 10 million years, it will have had enough time to have passed through hundreds of solar systems, if it's not picked up by anybody living in any of those solar systems. On this timescale, the plaque that is on both Pioneer 10 and Pioneer 11, the plaque is going to become essentially unreadable. The plaque tells anybody that picks up Pioneer 10, this is who we are compared to the scale of Pioneer. We've come from the third rock from the sun, of our particular sun. Where is our sun? It's indicated by this map, which is a pulsar map telling people where we are. Now, on the timescale of 10 million years or so, because Pioneer 10 and Pioneer 11 are basically flying through the interstellar medium, it is not empty space, it is not a true vacuum, it's full of microscopic dust particles. and over millions of years this plaque will become eroded by impact with those particles. So if it's not picked up in the first 10 million years or so, anybody who does pick up Pioneer 10 is going to find that this plaque is unreadable and won't be able to tell where Pioneer has come from. On a timescale of 10 to the 8 years into the future, we can ask ourselves what's the fate of Saturn's rings. But before we answer that, let's perhaps first think, where did they come from in the first place? It is possible that a moon, such as one about the same mass as the moon Mimas, it's possible that a moon of that size might have made Saturn's rings. When you look at a moon like this, you might think to yourself,
that's no moon, it's a space station.
Because it does indeed bear a certain resemblance to the Death Star. But a calculation has been done, a simulation credited on the left-hand side here. What would happen if you took a moon with a mass similar to Mimas, pulverized it, let's imagine it was hit by a comet or something like that. What would happen to all that debris? You might think, well, the debris will simply continue to orbit Saturn much like the original moon did. But actually what you find is, if you run the simulation, notice the timescale in the bottom right. It only takes a matter of days before you actually make a ring system. This is perhaps a little counterintuitive. What it means is all the individual tiny particles of debris that were generated are all interacting with each other so strongly they very quickly get spread out into the entire orbit rather than staying as a small dust cloud. And over time, all of these particles are slowly drifting in because they're all interacting with each other. They're drifting in towards Saturn. Over millions of years, it generates the ring system that we know and love and we see today. But the ring system is still changing. Those particles are still drifting inwards and ultimately raining down onto the surface of Saturn. So if you wait for another 100 million years or so, all of those ring particles will now be absorbed by Saturn and the rings will be no more. So for those of you who enjoy the sight of Saturn through a telescope, make sure you get in now. Don't leave it for another 100 million years. Also, on a similar timescale, now that we're thinking about the solar system, we should remind ourselves that although we think of the solar system as being clockwork, as indicated by an orrery on the left showing the planets and a tellurian on the right showing the moon around the Earth and the Earth around the sun, these things tend to kid us into thinking that the universe, or at least the solar system, is clockwork. And we should remind ourselves that we can indeed predict the positions of planets for centuries or thousands or tens of thousands of years into the future, but we can't predict these things indefinitely. On this sort of timescale, 100 million years or so, the solar system is effectively chaotic. We can't tell where the planets are going to be. Actually, we can't even tell how many planets there are going to be on this timescale. Much like the weather is predictable over a few days, but unpredictable over a few months, the same is true of the solar system. We can work out where the planets were thousands of years ago, we can work out where they will be in thousands of years, but we can't predict indefinitely into the future. Ultimately, the system of so many objects orbiting the sun is a chaotic system. On a timescale of 10 to the 8, still 100 million years into the future, we know that's roughly how long it takes the Earth to go once around the Milky Way. There's us, positioned approximately in between some of the dense spiral arms making up the Milky Way. But on a timescale of 100 million years or so, we are going to move from an area between spiral arms, a relatively low density region. We are going to move into one of the spiral arms, which is a higher density region. In other words, we're going to have a lot more stellar neighbours on a timescale of 100 million years or so. What are the consequences of having a lot more stellar neighbours? Well, there are effectively two consequences. One we've already mentioned, and that is if we have a lot of stellar neighbours, they are going to be close to us. One could easily bump into us in the sense that it could nudge the Oort cloud and send a lot of comets or asteroids heading our way. If we look at the fossil record, we see evidence of extinction level events, these spikes in the number of extinctions of species as a function of time in terms of millions of years before the present. We can see that there have been lots of extinction level events over the last 500 million years or so. Not regularly every 100 million, it's not quite that regular, but certainly on average, once every 100 million years or so, we have an extinction level event. The last one, labelled KT on the right-hand side, that's the boundary between the Cretaceous and the Tertiary eras. That's the one that killed all the dinosaurs. So having lots of stellar neighbours means that we're much more likely to have an impact from one of these asteroids or comets kicked out of the Oort cloud. And so we can predict that on this timescale, we're likely to have another extinction level event. Now, we don't know what that's going to look like. This, of course, is just an artist's impression of a huge rock heading towards the Earth. If we look at the left-hand side, it seems to be heading towards Italy. Now, that's bad news for Italy. But if the rock is big enough, it's bad news for the entire planet. It doesn't really matter where it's going to hit. A significant number of species will come to an end. The real question is, will that include us? Very difficult to predict. We need, in the next 100 million years or so, to get our act together in terms of trying to deflect any incoming asteroids or comets to make sure they have minimal chance of hitting the Earth. The second reason why having lots of stellar neighbours could be an issue, apart from the fact that we are going to have a greater probability of an extinction level event, having more stellar neighbours means that it's much more likely that one of those stellar neighbours is going to go supernova. At the moment, if you look at how many stars there are within a few, let's say 10 light years for the sake of argument, there aren't that many stars that close to us. And none of them are really massive stars that are likely to go supernova. But if we have many more neighbours, then it's much more likely that one of our neighbours is going to be a supernova, and that could be a problem. A supernova within 100 light years of us could be a danger to Earth simply because of the amount of radiation it will produce. And it's been estimated that a supernova within 20 light years of us might conceivably produce so much radiation it could end all life on Earth. Now, if that sounds a bit alarmist, bear in mind that we know that supernovae have gone off relatively close to Earth in the past. Supernova within about 100 light years or so will leave deposits on the Earth of a particular isotope called iron-60. This is made by supernova because they are such energetic events, and we know of no other way that this particular isotope can be made. And this isotope decays, or changes if you prefer, from iron into other elements, cobalt and then nickel. And it does so over a few million years or so. That means if we see iron-60 in the sediments of Earth, because we know it changes over millions of years, this iron deposit could not have been there since the Earth began. It could not have arrived 1 billion years ago because none of it would be left. Any iron-60 we see must have come from a relatively recent, meaning only a fraction of 1 billion years or so, a relatively recent supernova that went off relatively close to us. So it's happened in the past. We think it could happen in the future. Still on a timescale of 10 to the 8 years, 100 million years into the future, all of this time, the moon has been tugging on the tides of the Earth and slowing the Earth down. Through so-called tidal friction, the moon has been robbing the Earth of some of its angular momentum, some of its spin if you prefer, and slowing it down, hence the days getting longer. And in the process, the moon's orbit has been getting larger. The length of the day is now so slow. The length of the day is 25 hours. There's no point even thinking about leap seconds anymore. We just have to abandon the idea of a 24-hour clock. But what's going to happen because of the moon's orbit changing? Well, at some point, the moon's orbit will be so large in terms of its radius, in terms of the distance from the Earth to the moon, the disk of the moon as seen in our sky will no longer be large enough to cover the sun. So from this point onwards, there will be no more total eclipses of the sun, no more total solar eclipses, as indicated on the left-hand picture, where the disk of the sun fortuitously is just large enough to cover the disk of the sun. We will still have partial eclipses, and we still have annular eclipses where a ring of light would be visible around the smaller disk of the moon. So again, for those of you who like solar eclipses, well, get in now, because you won't have any more after 1 billion years or so. The second consequence of the moon moving away from the Earth, apart from no more solar eclipses, is a rather serious one, and that is the moon has a stabilizing influence on the tilt of the Earth, the so-called obliquity of the Earth's axis. Being relatively close to the Earth means that it tends to sort of lock, if you like, or at least stabilize the tilt of the Earth. It's roughly 23.5 degrees, and we don't think it's changed by much more than about 1 degree either side of that. The little cartoon on the left shows the sort of variation that we think has occurred in the past. And it's mainly not been any more variation than that, simply because the moon is close enough to stabilize the axis. But if the moon moves away from the Earth, which it will continue to do for the next billion years or so, at some point it will no longer keep the Earth's axis locked in position, and the Earth's axis could in principle flail around and change erratically. And that, of course, will produce violent changes in the Earth's climate. On a scale still of 10 to the 9, there will be changes to Voyager's gold disk. On board there's a gold disk, as indicated on the right-hand side, a phonograph, and after 1 billion years or so, we think that will be almost impossible to play. It's simply a question of how fast the atoms in this particular metal will evaporate and disappear. Now, why do we think that Voyager's gold disk is going to last 1 billion years rather than Pioneer's plaque, which only lasts some few million years? Well, Voyager's gold disk is going to last longer, we think, simply because it is protected behind a cover. And so the cover is going to take the impact of particles in the interstellar medium and is going to protect the disk. Well, that's great, except for the fact that the cover actually contains the instructions for how to play the disk. But let's assume if Voyager's disk is picked up by some civilization. Remember, after 10 to the 9 years, it will have been through thousands, many thousands of different solar systems. Perhaps one of those solar systems is populated and the inhabitants will pick up the Voyager spacecraft and the disk. Maybe, if they're intelligent enough, they can figure out how to play the disk, even if the cover itself makes the instructions unreadable. Still on a timescale of a few billion years, the sun will slowly change. It hasn't yet reached the red giant phase, but it's on its way. The sun's luminosity will start to increase as it evolves and starts to move towards its red giant phase as the nuclear fuel inside slowly starts to run out. The greenhouse effect, because of the increasing luminosity of the sun, the greenhouse effect is going to drive the surface of the Earth up to a relatively balmy 80 Celsius or so. We're going to lose the oceans and the surface of the Earth will become uninhabitable. Going underground is not going to help. I think at this point we're going to have to leave the Earth and then wait for it to cool down and come back later when it's cooled off a bit. We think the sun, when it does go through its red giant phase in a few billion years, is going to expand until the radius of the sun is comparable to the radius of the Earth's orbit. And so the question is the Earth going to be engulfed by the sun? Looking at it, it looks like this could be a problem for us. Some people believe the Earth is going to be engulfed by the sun. It's almost certainly true that the radius of the sun, when it becomes a red giant, is going to be comparable to the Earth's orbit. But that doesn't actually mean that the Earth will be engulfed, because as the Sun expands, there will be a very strong solar wind as it becomes a red giant, and the Sun will lose mass. If the Sun loses mass, then the Earth, because the Sun is pulling on the Earth, keeping it in orbit, the Earth will drift away to a larger orbit. So this cartoon on the left shows what might happen. As the Sun gets larger, it gets lighter, and so the Earth drifts away. So eventually the Sun does indeed engulf the original orbit of the Earth, but the Earth isn't there anymore because of the lower mass of the Sun. And perhaps the Earth could end up somewhere closer to the orbit of where Mars is now. By no means certain, but perhaps the Earth will survive. Let's assume it does for the time being. Having survived the Sun going through a red giant, the Sun then changes to a white dwarf. The Sun will slough off its outer atmosphere to become a planetary nebula, and what's left is a white dwarf star. But the Earth has more problems ahead of it. If it survives the Sun going through a red giant phase and then becoming a white dwarf, the Earth then finds that the core of the Earth cools down to the point where it loses its magnetic field. The core of the Earth is currently molten, and it's not being kept molten by heat from the Sun, it's being kept molten by the heat generated by radioactive elements dumping their heat in the core of the Earth, keeping the Earth's core molten, and a rotating molten core is a dynamo that generates a magnetic field. Once that radiation is no longer enough to keep the core molten, then we no longer have a dynamo, we no longer have a magnetic field. And the magnetic field is partially responsible for protecting us from some of the radiation coming from outside, some of it from the Sun, a lot of it from the rest of the cosmos. It's thought that perhaps this is what happened to Mars. Mars is a smaller planet. Maybe its core cooled a long time ago, and when its core froze, it no longer had a magnetic field, it could no longer have protection against cosmic radiation, and it was stripped of its atmosphere. Maybe ultimately that's what's going to happen to the Earth. They say bad things happen in threes. If the Earth survives the Sun going through a red giant phase, if the Earth survives the loss of its magnetic field, then there's a third problem it has to contend with. And that is the Andromeda Galaxy is going to come crashing into the Milky Way on this sort of timescale, a few billion years. Now this is going to be great for astrophotographers because instead of photographing small galaxies which need a telephoto lens, if you wait for a few billion years, the Andromeda Galaxy is going to come towards us and is going to be so big in our sky, you're going to need a wide-angle lens to get it all in. It's going to be spectacular. When the Andromeda Galaxy passes through the Milky Way, there is going to be a riot of new star formation. It's unlikely that one star hits another star, so the Andromeda Galaxy is probably going to come out the other side, and the Sun is probably not going to hit any of the stars in the Andromeda Galaxy. If the Sun gets pulled out of the Milky Way, well, the planets will simply probably go with it. After a few billion years, the two galaxies are going to settle down, and the merger of the two galaxies won't produce a rather beautiful spiral galaxy that we now have. It'll produce a rather more amorphous blob of a rugby ball shaped elliptical galaxy. Perhaps we will have two nuclei for a little while, the nucleus which was the original supermassive black hole of Andromeda, and another nucleus which is the original core of the Milky Way. It'll take a few more billion years before those two supermassive black holes eventually merge together as one. On a timescale of 10 to the 11, so we're now talking about, 100 billion years into the future, the slow dance between the Moon and the Earth finally comes to an end because they are now locked together because one day is equal to 1 month. Remember, the tides of the Moon raising tides on the Earth has slowed the Earth down and sent the Moon to a larger orbit. So now the Earth is spinning such that one day, the length of time it takes to spin once, is equal to 1 month, the length of time it takes the Moon to go round the Earth. So the Earth is now tidally locked to the moon. The same face of the Earth will always face the moon, and there will be one half of the Earth which never sees the moon. This is the exact mirror of what the moon has been doing for billions of years. Remember, we can see only one face of the moon. We can't from Earth see the far side. Eventually that will be the same in reverse. As seen from the moon, you will only ever see one face of the Earth. And this picture on the right, by the way, which looks like a clever use of Photoshop, is a genuine picture. It only looks false simply because it's a picture taken from a long way on the other side of the moon. So we're looking at the full Earth and the full moon, but we're looking at the full moon on the far side, not on the near side, which is why it doesn't look familiar to us. We're now thinking of 10 to the 12, 1 trillion years into the future. We've already said that the Milky Way and the Andromeda Galaxy are going to merge together. If we look at what the immediate vicinity of the Milky Way is, there are lots of small galaxies. So the local group, our immediate neighbours, we have a few big galaxies, but most of the galaxies are rather small satellite galaxies. The Milky Way is going to hoover up all of these galaxies. So we already know that the Milky Way is going to collide with M31, the Andromeda Galaxy. Eventually M33, the Triangulum Galaxy, will also get absorbed, and everything in the local group will merge into one mega galaxy. It won't be a spiral as indicated by this little icon. It'll be probably an elliptical galaxy. But what happens to galaxies that aren't coming together because of gravity? What happens to those? Well, the universe will continue to expand as far as we know, and those galaxies will get further and further and further away from us. Now, in a lockdown challenge in 2020, I decided to try and image a very remote galaxy, a quasar, which is a galaxy with a very bright nucleus. I tried imaging one of these quasars, even without a telescope. And I found that even if one of these quasars is receding from us at twice the speed of light because of the expansion of the universe, it can still be imaged. That's the situation at present. If we look, for instance, on the right-hand side at a Hubble deep field or a Hubble ultra deep field, we see thousands upon thousands of galaxies. There might also be one or two stars in that field of view from our own galaxy, but most of what we can see there are more distant galaxies. But as the universe continues to expand, in 1 trillion years or so, all of these galaxies are going to be so far away from us, we won't be able to image them. In fact, a hypothetical civilization that comes along in 1 trillion years and builds themselves a telescope and looks out into the universe, what are they going to see? They are only going to see stars in their own galaxy. They will come to the conclusion there is no such thing as any other galaxies in the universe. Not because their telescope is not good enough or hasn't got a large enough mirror, simply because it will be impossible to see galaxies once they've moved outside your horizon. So it's sobering to realise that we only know that there are billions or possibly even trillions of galaxies in the observable universe simply because we can observe them, and that will not always be the case. I said a little while ago that when we think about the beginning of everything, it actually only took 3 minutes to make all the hydrogen in the universe, according to our current understanding in the Big Bang theory. So 3 minutes to make all of the hydrogen. But now, 1 trillion years later, it's starting to run out. There will come a time when there's no more hydrogen to make new stars. Now, some people believe, this is a little bit of an aside, but some people believe maybe you can make stars without starting with hydrogen. Is it possible to use heavier gases to make stars rather than start with the lightest and then build up slowly? Use hydrogen to make helium, use helium to make carbon, etc. Can you start with something heavier in the first place? Some theorists believe maybe you can make stars out of heavier gases. Some believe you might even be able to make a star with fusion reactions, nuclear fusion reactions in the core, but surface temperatures even lower than a red giant which has a surface temperature of thousands of degrees. Maybe you can make one with a surface temperature of only hundreds of degrees. Is it possible actually to make a star with nuclear reactions at the core but a surface temperature as low as 0 Celsius, where ice would form? Frozen stars. And when I say frozen stars, no, I'm not talking about the Disney version of Frozen. If that's the picture you've got in your head, then let it go, because what I'm talking about is stars in which they are cold enough at the surface for ice to form. A pretty amazing idea, but not everybody agrees that's possible. Most people think once you've no longer got hydrogen, you can't make any more stars. Now, before we can go any further, and yes, I know the red rectangle is on the right-hand edge, but no, we haven't quite done yet. Before we go any further, we have to simply think about what the universe as a whole is doing. What is the expansion of the universe? What does it look like now? And what do we think it's going to be in the future? Well, there are a number of different possibilities. The vertical axis here is how big the universe is. Just take two arbitrary galaxies a long way apart and use that as a scale factor. The horizontal axis is time, where now is indicated on the bottom axis. So that circle is where we are. The universe has a current size of 1 and we are at now. You can see 4 different coloured lines. The 4 coloured lines show us how the universe has changed and will change according to how much stuff we think there is in the universe. Notice that each of these coloured lines is different and gives us a different 0. The age of the universe depends on how much stuff there is in the universe. We know how fast it's expanding now, but how fast it used to expand in the past and will expand in the future depends on how much mass and energy there is in the universe. If there was an awful lot of mass in the universe, there would be so much gravity, the expansion of the universe would be stopped and gravity would pull everything back again, and there would be a big crunch. So the orange corresponds to the universe expanding, stopping its expansion and then contracting back to a big crunch, a so-called closed universe. But we don't think there's enough mass in the universe to actually do that. When I was young, we used to think that we were on the green line, but now it seems like we're on the red line. The amount of matter and energy in the universe implies that we're on the red line, a universe that's 13.8 billion years old. And notice that the expansion is not only continuing, look at the slope of that line. It looks like the expansion is getting faster and faster and faster. And to the best of our knowledge, nothing looks like it's going to turn that around. So it looks like the universe will continue expanding forever. And in order for me not to keep you until midnight, we're going to change the scale on the top here, and notice the numbers are now very much bigger. Each small box in the timeline above now means 1,000,000 times further into the future, not just 10 times. So we're talking about ridiculous numbers, a zillion years into the future, a gazillion years. I don't even know what labels we should be giving to these things. 10 to the power, very big numbers. So where did we leave things before we took this little aside and asked us what the universe is doing? We said that after 1 trillion years or so, the universe is running out of hydrogen. As far as we know, you need hydrogen to make new stars. So if the universe is running out of hydrogen, we have to remind ourselves that stars don't live forever. Stars might live, some of stars might live for many, many, many trillions of years, but they don't live forever. So what happens when the universe runs out of hydrogen? The age of starlight will come to an end. There will be a point at which there are no more stars shining because nuclear fusion is generating energy which allows the stars to put out heat and light. The stars will still be there in the sense that even though they're no longer shining, these dead stars will continue to orbit in their galaxies. So there are a number of stars in this category: white dwarfs, neutron stars, and black holes. It may sound odd to talk about white dwarfs shining or not shining when it's clear that they are white, so surely that means they are shining. Well, only because they are hot. They are not generating energy due to thermonuclear fusion. For a little while they'll stay hot and continue emitting light, but they will simply cool off. With no nuclear reactions to keep them hot, white dwarfs won't stay white for very long. They will cool down until they are, well, let's just call them black dwarfs. Basically, lumps of matter that are not shining. They become colder and colder and colder. Some stars will be ejected from the galaxy and some will be eaten by the supermassive central hole, and supermassive black hole at the centre of what we think is every galaxy. So the way that matter gets funneled into the supermassive black hole at the centre of the galaxy, well, we're not sure of the exact mechanism, but for instance, we have looked at magnetic fields in other galaxies. For instance, this one mapped out by SOFIA, the Stratospheric Observatory for Infrared Astronomy, that's the telescope in the back of a jumbo jet there. This has worked out what the magnetic fields are, and it follows this rather complex pattern shown by the left-hand animation. And we think that matter, that means gas and other stars, will be funneled down these magnetic field lines and effectively feed the supermassive black hole at the centre of the galaxy. Now, on even longer timescales, again, we're not too sure what's going to happen. We know that atoms are made of positively charged protons and negatively charged electrons buzzing around the nucleus. But we think that it's possible that positively charged protons in the nucleus of atoms, it might be that they change. It might be that they decay, and as a result, every atom in the universe will fall apart. Now, we don't know whether this is going to happen, and if it does happen, we don't know the timescale on which it will happen. It's simply been calculated that it's not likely to happen on a timescale less than 10 to the power 36 years. But it might happen on longer timescales, in which case there will be no atoms in the universe at all. Even if this doesn't happen, atoms aren't going to last forever. They may survive for a little while longer if protons don't decay, but given that the only atoms in the universe are in these black dwarfs, eventually black dwarfs will evaporate. It's a quantum mechanical process that I'm not going to describe, but basically no atoms will exist beyond this point in the universe. Remember, the only types of star that were left were black dwarfs, neutron stars, and black holes, and neither neutron stars nor black holes contain or made of atoms. We think that black holes will merge with each other. Remember when we talked about galaxies colliding with each other, galaxies merge together if they are close to each other in terms of gravitational pull. It is thought that whole loads of clusters of galaxies will merge together, and black holes will mean, the merger of black holes will mean that we end up with black holes not that are simply millions or perhaps billions of times the mass of our sun. We could see monster black holes whose mass are some trillions of times the mass of our sun. But even black holes do not last forever. Black holes are not eternal. Black holes evaporate, or at least we believe they evaporate. We haven't seen any do this, but it's a hypothesis which Stephen Hawking came up with and a lot of scientists agree with. But you do have to wait an awfully long time to expect any black hole to evaporate. So why do they evaporate? Let's just very briefly give the bare bones argument that Hawking came up with. Quantum mechanics allows particles and antiparticles, in other words, bits of matter and bits of antimatter, to be created from borrowed energy. You borrow energy from nothing, you can use it to make particles and antiparticles, and they will annihilate and pay back the borrowed energy on ridiculously short timescales. You generate energy, you generate particles, they annihilate, you get the energy back again. So that's borrow, make stuff, and then they annihilate and the energy is repaid. But Hawking said, yeah, but what happens if you do that just outside the event horizon of a black hole? What if you create a particle and an antiparticle just outside? Let's imagine that's the event horizon. It is possible that you borrow some energy, you make particle and antiparticle, whoops, one has gone into the black hole and the other one hasn't. So that means that the particle that's left can't annihilate with its partner, if you like, because the partner is now inaccessible. So it's as if some radiation, some particle, which ultimately would produce radiation, has left the black hole. And it's that makes us think that black holes evaporate. There's a net flux of particles radiating from the event horizon. We call it Hawking radiation. And it just so happens that the radiation increases with decreasing mass. So as black holes evaporate, as they get smaller and smaller and smaller, they radiate more and more and more. Large black holes will take a long time to evaporate. Small black holes will evaporate relatively quickly. So the radiation levels from any particular black hole will increase as time goes by until the black hole disappears in a flash of radiation. And on this ridiculously long timescale indicated by the red rectangle, we think that even the largest supermassive black holes lurking at the centres of most galaxies, even they will evaporate eventually. But it will take, indeed, trillions of times longer than the smaller black holes that result, for instance, from stellar collapse. So have we reached the end of time? Well, we've reached the end of the timeline at the top of my slide there. If we think about the number such as 10 to the power 100, 10 to the power 100 is a Google. No, not that Google, that's simply a misspelling of the actual Google, which is 10 to the power 100. We think that after a Google years, it is quite probable that the last black hole in existence, no matter how big it could possibly be, with the slowest possible evaporation rate, even the largest black hole will have evaporated after 10 to the power 100 years. So after this, nothing happens. There is no matter left anywhere. There's just radiation floating around the universe. So you could argue from this point onwards, the passage of time becomes essentially meaningless. Now, 10 to the power 100 is a ridiculous length of time. And I don't normally show the zeros, but I'll make an exception for 10 to the power 100 and remind ourselves just what we're talking about. 10,000 million, oh, you can do it yourself. It's an awfully long time. Much, much larger than, for instance, the age of the universe by many, many, many orders of magnitude. So large, we can basically not get our heads around it. We can do the maths. We can't visualize that number, but we can still do the maths if we need to. So have we reached the end of time? Well, eternity is a very long time, especially towards the end. Woody Allen. My favourite cartoon is XKCD, and they came up with a way of thinking about the human condition and how a human lifetime fits into the sort of times that we're talking about. They say a human is simply a system for converting dust billions of years ago into dust billions of years from now, via a roundabout process, which involves checking email a lot. That's one way of thinking about a human lifetime in terms of the lifetime of the universe. So for those of you who are now thoroughly depressed that everything is going to come to an end, let me finish with a slightly more upbeat epilogue. You could say that we live in a golden age. The sun is middle-aged and well-behaved. The moon is at just the right distance to stabilise the Earth's axis and hence to stabilise the Earth's seasons and give us a nice environment. It also gives us the spectacle of a total solar eclipse because of this fortuitous match between the size of the moon and the size of the sun in our sky. Thanks to evolution, we are able to explore and discover and understand the universe. And we can do that by building machines to go visiting our closest neighbours, or we can build telescopes that allow us to see billions of galaxies that are potentially billions of light years distant. But we couldn't have done this in the early universe. Humankind could not have arisen in the very early universe. We needed generation upon generation of stars to take the hydrogen and do nuclear fusion to make the helium, and then use that helium to make carbon and nitrogen and oxygen and calcium and phosphorus and iron. All of the elements that make us us. We needed many, many generations of stars to give us the right conditions for life as we know it. And we've just seen that in the future, trillions of years from now, the universe will be dark and the universe will be boring. So you could say the best time to exist is now. Thank you for listening.